All right, so I just made a big deal about how if you know K, you know everything. Now let's do some examples. Remember that? All right, so we already figured out this was the restoring force, right? F equals minus constant R, X, whatever you want to call it, right? So this is F equals minus Kx. So for that one, the K is mg0 over the radius of the Earth. Right? So the mass of the object times 9.8 meters per second squared divided by the radius of the Earth. Okay, well, hey, we're done. The period is 2 pi square root m over k. So let's put in k. So we have 2 pi square root m over k. So k is mg0 over the radius of the Earth. Well, that's 2 pi square roots of re, m's cancel, over g0. All right? Now, wouldn't you like to know what that is? Of course. So you plug it in. They give you the radius of the Earth, right? We know what g0 is. So you plug it in, and you get 5067 seconds, which is about equal to 84 minutes. Now, I hope you're impressed. So what does that mean? I mean, that means if you had a tunnel through the center of the Earth, right, and you ignored, air resistance and heat and all the goofy things, no lava and anything, all right? If you just had a tunnel through the center of the Earth, and you dropped something, the period, the time from this to that, the period would be 84 minutes. Now that's surprising to me. I mean, that's super surprising to me. But look at how simple that was. Once you write it in the right form, F equals minus K variable, and you figure out the K, then you just use this formula to figure out the period. Bingo! That's it. You're done. So that's what I mean. The whole point of this simple harmonic motion is figuring out is showing that something undergoes simple harmonic motion, and then finding out the K. Once you know the K, you know everything. Everything. It's awesome. Okay, let's do the pendulum. Okay, we did the pendulum. So here we had. Okay, so we figured out that the force equals minus K variable. F equals minus constant variable, right? And so for the pendulum, K was mg over L. All right. Well, the period is 2 pi square roots of m over k. That's 2 pi square roots of m. Put in k. K is mg over L. So the m's kill. You get 2 pi square roots of L over g. There you go. No, hardly any work at all, right? So that's the how long it takes to make one cycle. Start here. Again, small angle approximation. Now, most people, if you were to ask most people what the period of the pendulum would depend on, most people would say it depends on the mass. It kind of seems reasonable, don't you think? But in fact, does it depend on the mass? Not at all. All it really depends on is the length of the string. So I have a little demo. Okay, so, all right. Now, when we say the length of the string, we really mean from here to the center of mass of the mass, okay? So here to here. So these two basically have the same L, all right? Now this is 200 grams. This is, I don't know, 10 grams, all right? So 200 grams, 10 grams. Now this is the same mass as this, all right? So let's just do these. So we know, because of the formula, that the mass is irrelevant. So here's the same mass but different length of the string. So watch. So let me do that again. I should have brought a clamp. Anyway, you can see that I certainly don't have the same period, right? No way. Okay, but now we're going to take these two. So 200 grams, 10 grams, but pretty much the same length of the string, right? So watch. What do you say? Same period, right? So what do you know? The formula works. Okay. So this is one of these surprising things. You know, again, most people think it would include a mass, but it doesn't, right? It doesn't. Okay, so, all right, so what am I saying? If you can show something undergo simple harmonic motion, then you figure out the K. If you know the K, you're done. You know all of the kinematic variables, you know the period, and you know the frequency. So you're done. So it's awesome. All right, here's a question for you. So there's the equation for the, so this is the period for a pendulum, yeah? So there, okay, all right. A ball on a massless rigid rod pendulum oscillates as a simple pendulum with a period of 2 seconds. If the ball is replaced with another ball having twice the mass, what will the period be? So pause your video and figure it out. Okay, we're back. So is there a mass in that formula? No. So does the period depend on the mass? No, I just showed it to you. So what's the answer? 2 seconds, right? 2 seconds. Okay, now let's get a little harder. On planet X, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the pendulum is taken to the moon of planet X, where the free fall acceleration g is half as big, what's going to be the period? So pause your video and figure it out. A little bit of math, or figure it out. Okay, so we're done. I mean, we're back. We're not done. We're back. So the period is 2 pi square root L over g. Now what they're saying is that the g becomes g over 2, right? So the g becomes g over 2, right? So that's the same thing as saying 2 pi square roots of 2L over g, right? So we have this extra square root of 2, right? Agree? So in other words, the original period was just 2 pi square root of L over g, and that was 2 seconds. But now we have the new period is 2 pi square root of 2L over g. So that's the same thing as square root of 2 times 2 pi square root of L over g, or square root of 2 times 2 seconds. So work it on your calculator. Square root of 2 times 2 seconds, it's the 2.8. Okay? So there you go. So the only thing it depends on, the L, the length of the string, and the acceleration due to gravity. All right. When we did motion, you know, we did linear motion, and then we did rotational motion. Well, let's see if we can use rotational motion. Of course we can. So let's figure out the rotational equations for simple harmonic motion. It's wonderful. You're going to love it. Okay, what's the rotational analog of force? Torque. What's the rotational analog of x? Theta. What's the rotational analog of m? I, right? Rotational inertia. So all you have to do is substitute. So there you go. So torque equals minus k theta, angular displacement. That's wonderful. And then this, we're just going to have an I here, and just like over there, just an I. So period 2 pi I over k. Frequency 1 over 2 pi k over I. That's all you have to do. That's what I was, when we were learning about torque and rotational inertia, you know, I kept emphasizing that this is the replacement for force, that's the replacement for x, that's the replacement for mass. So if you remember that, it's really simple to get these equations. Okay, wonderful. All right, so what do you say we do an example with this? So this, you know, we don't have a string, right? It looks like a bowling ball. So this is called a physical pendulum. And of course, it's much more complicated, right? Because it's not just a mass on a string. It's like a bowling, not a bowling ball, a bowling pin, all right, bowling pin. All right, let's do it. So the question is, we want to figure out what t is. So we're going to use that equation. So t equals 2 pi square root of I over k. Okay, ready, go. Well, we got to figure out k. Well, first of all, we got to even figure out if it undergoes simple harmonic motion, right? If it doesn't, we'll just forget it. Okay, so we want a restoring torque, right? And remember, the torque equals the perpendicular r, F times r, or F times r perp, whichever you like. So, look at the picture, and what is the restoring torque? Remember, this thing is going like this. You know, it's going like, all right? So let's say it's going like this. So what's the restoring force? Just like before, Fg sine theta. So if this is the force line, this is the lever arm, right? Perpendicular distance from the force line it's this d. Okay? Awesome. So the torque, so the restoring torque is Fg sine theta times d. Now what did I forget? Something very important. What did I forget? I did it on purpose, but what did I forget? The minus sign. Okay, you've got to put that minus sign. If the thing is going in this direction, the restoring force is in this direction. If the thing is going in this direction, the restoring force is that direction. So it's always opposite. And of course, we can write that as minus mgd sine, yeah, that's pretty nice, right? Write it like that. So Fg is mg. So minus mgd sine theta. Okay. Wow! Does this undergo simple harmonic motion? Is this a F equals minus kx? Or is it a torque equals minus k theta? No, because we have a sine. So what do we do about it? Just like we did before, right? You just restrict the motion. You use small angle. So small angle approximation. Small theta approximation. So sine theta equals theta. So wonderful. So torque equals minus mgd theta. Right? There you go. So this is the one that we really like, right? So this is the one we like. Now, what's the constant? M is a constant, G is a constant, D is a constant. So let's do that, make it obvious. So now we have torque equals minus constant variable. Simple harmonic motion. Right? So the K is just mgd. All right. So let's do it. So the period is 2 pi. Okay, now we'll just put I for now, just over mgd. Okay? And that's it. All right? Now, you look at that and say, oh my gosh, it depends on mass. No, it doesn't. Because the I, remember, I is the sum of mr squared, right? And so there's a mass here, there's a mass here, the masses will cancel. But anyway, that's how you figure out the period. So, you know, we would have to know what the rotational inertia of this crazy bowling pin is, right? But this is good enough. So I hope you understand. You know, once you show it undergoes simple harmonic motion, you figure out the K, then you can figure out the period without hardly any work at all. All right, so there you go. So all we've done so far is ideal situations. Well, sorry to say this, but the real world isn't ideal, you know? And for the ideal case, again, the amplitude does not decrease with time. It's constant. But in a real case, you know, the amplitude decreases with time. So, this is from lab, by the way. This is called, when you include friction and internal resistance and all that, it's called a damped oscillation. So this is reality, right? I mean, think of your shock absorbers. They're damped, right? Can you imagine being in a car if you had ideal shock absorbers? You know, the bouncer would never stop. So you want damping. So this is a damped oscillation. You can see the amplitude decreases with time. Look at the time. I mean, you know, 60 seconds, that's a minute, that's 2 minutes, right? So, okay. So here's a nicer picture, all right? So damped oscillation. So we start out with amplitude A, right? And then it just kind of decreases. Okay, now we're going to do a lot of math. So beware, make sure you're alert. This is the math part. Okay, here we go. All right, so certainly the energy is not constant, right? The energy decreases. All right, what we got to do, believe it or not, is we got to come up with an equation for this. All right, that's what we got to do. And if you've studied your review sheet, your math review sheet, you should know how to do it. Okay, let's do it in 2 parts. So what's the equation? You weren't supposed to see that? What's the equation of this up in the blue, the up and down part? What does that look like? Cosine, right? Goes A, you know, it just keeps, you know, it's a cosine. So the blue part is the cosine. All right? What's this? So it's on your math review sheet. That's that e to the minus constant times time. So b is a constant, just a number, you know, right? So b is just a number, right? So this is your e to the minus time, and this is your cosine. Now, I said earlier that we're going to use this a lot in physics, this e to the minus time, or e to the minus constant times time. So I just want to show you a graph. So this is the function, right? Y equals e to the minus constant times t. B is just a number, okay? Constant. So here's the graph, e to the minus 25t. You can see, wow, it just dies really, really quickly, right? It just goes to 0 super fast. Here's e to the minus 5t. Not so fast, but still pretty fast. Here's e to the minus t, like that. Here's e to the minus 1/5 t, you know, kind of dies off slowly. Here's e to the minus 1/25t, you know. All right? So that's just, like I say, if this is a big number, e to the minus 25t just dies off super, super quickly. So like if you wanted a shock absorber, you know, you want the oscillations to die off quickly, right? You'd want something like this. You certainly don't want that. Okay, anyway, so back. So how do you get the equation of this thing? Well, we have a cosine, and we have an e to the minus bt. How do you get the whole thing? You just multiply them together, right? So x equals, here's your a cosine 2 pi ft, and here's your e to the minus bt. So this equation gives you the x for anywhere you want, for any time. All right? So that's pretty awesome. Now, what is the maximum x? So this is a math question. So you look at this equation. What's the maximum x? Well, what's the maximum cosine? You know, cosine goes between 1 and minus 1, right? So that means this here is the maximum x. So the maximum x is a, the amplitude, times e to the minus bt. Now, there's a really smart way of writing this. And it might look ridiculous at first, but it's really smart, trust me. And we're going to do it again and again and again in Physics 106. So I want to go through it. Okay? So, all right. Let's do a little algebra, which you're going to think is silly, but just hold your horses. All right. So, you know, here I have a e to the minus bt. Well, can't I write it like this? E to the minus t all over 1 over b? I mean, yeah, I can, right? That's correct. It's correct math. You might think, why would anybody with a half a brain want to do that? Well, just have patience. Okay, so it's correct. Now, what are the units of this exponent? What are the units here? Well, you know, you can't have an e to the kilogram or to the second. These are unitless, okay? There's no, I mean, all right, they're unitless, right? Just do the math, okay? So this here has no units. This here has no units, all right? Wow. Time, here, let's get rid of this. Time, this is a t, right? This is in seconds. So what has to be the units of b? What has to be, well, sorry, what has to be the units of this? So this whole thing has no units. T has units of seconds, so it has to be the units of 1 over b. Seconds, right? Because seconds over seconds has no units, all right? So 1 over b has units of seconds. So come on, let's make life nice. Let's just say that 1 over b equals something called tau. That's the Greek letter tau. It looks like a T, right? And it has units of seconds. Now, why? Well, why do we do anything? To make life easy, okay? So, all right, so what we're going to say is we're going to say 1 over b equals tau. So therefore, we're going to write this as a e to the minus t over tau, because 1 over b equals tau. So t has units of seconds, tau has units of seconds. So tau is called a time constant, and it's in seconds. And why is it nice? Here's why it's nice. So I have x as a function, x max as a function of time equals a e to the minus t over tau. Now, here's what's nice about it. Let's say that the time equals tau, whatever that is, 2 seconds, I don't know, whatever it is, you know. So then I have x of tau, that's a tau, sorry, equals a e, well, t is tau, so I have minus tau over tau, which is minus 1, right? So I have e to the minus 1. So that means that x equals a e to the minus 1, which is a over e to the 1, or a over e. Now, most people who do math know what, I mean, this is the same thing as, you know, a times 1 over e, right? Well, most people that do math a lot know what 1 over e is. It's 0.37. Okay, 1 over e is 0.37. So that means that when the time equals tau, the x max is just 0.37 times the amplitude. Okay, let's do the next one. Let's do at time equals 2 tau. Well, then x at 2 tau equals a e to the minus t, now time is 2 tau over tau, which is a e to the minus 2, right? Which is a over e squared, and which again is a over 1 over e squared. And most people that do math know what 1 over e squared is. It's 0.13, okay? So all I'm saying is, if you put time in terms of this tau, it's super easy to calculate x max, because it's going to be a e to the negative 1, a e to the negative 2, a e to the negative 3, a e to the negative 4, and it's simple. And again, so that's why we do it, okay? And you're going to see that again, 106, so remember it, all right? Okay, last topic. We want to talk about driven oscillations and resonance. Okay, so look. This thing, I pull it down. Eventually it's going to stop, right? Well, what if I attached an oscillator to it? You know, then it wouldn't stop, right? Now, if I really don't want it, okay, that's fine right there. Now, let's say, so yeah, so this is like the natural frequency of oscillation, and then if I put a machine on it, I would call that the driven frequency, right? You know, the frequency of the machine, or me, is the driven frequency, okay? Now, actually, you guys already know this. Let's say we have a child on a swing set. Now, if you just let the kid alone, the child is going to eventually stop and be unhappy, right? So what you want to do is you want to push the child, agree? So the child keeps swinging. Now, if you want the child to go really high, kid's a daredevil, you know, here's the natural frequency. So what's going to be your frequency? What's going to be your frequency of pushing? The same, right? You want to match your frequency, the driven frequency, with the natural frequency, okay? Now, when you have a situation where the driven frequency is exactly equal, so F driven equals F natural. When that occurs, that's called resonance. Why do we care about that? You just hold your horses and you'll see. All right? Resonance. So you can get really, really large amplitudes. Okay, now let's say you have like no damping or really small damping. Then the amplitude is going to get gigantic. The energy is going to get gigantic. Okay? So here's a picture. And there's two concepts in this picture. So you have to really be careful that you understand what's going on. All right, so what we're saying, we have some kind of system. I don't care. We have some kind of system where the natural frequency F0 is 2 hertz, 2 cycles a second. And then we have some kind of machine or something, and we can adjust the driven frequency. So see, this is the external frequency, the driven frequency. We can adjust it. 1, 2, 3. All right? So look, when the driven frequency is like 1, that's different from the natural, so we don't get resonance. Nothing really happens. The amplitude is not all that big. But look what happens when we get closer and closer to look at what happens when the driving frequency equals the natural frequency. We get resonance. So we have hardly any damping at all. Look what's going to happen to the amplitude. Wow, crazy, right? When we have medium damping, it's only going to go like this. When we have super heavy damping, it's not going to change much at all. Okay? But the point is, the amplitude is gigantic when the driving frequency equals the natural frequency. And again, that's called resonance. And this is nice because it shows, the damping, right? Now, I still haven't answered the question, why do we care? So here's why we care. Okay. So here's a glass. Well, the molecules in the glass move around, right? They have a natural frequency. Okay, so there's a horn or something. Music, natural, that's the driven frequency. So the frequency of the sound from the trumpet exactly matches one of the normal mode frequencies, the natural frequency of the goblet. The resonant vibrations of the goblet have such large amplitude that the goblet tears itself apart. It's cool, right? How about this? And this is really kind of interesting. Resonance in mechanical systems can be destructive. Some years ago, vibrations of the engines of a particular airplane had just the right frequency to resonate with the natural frequency of its wings. Large oscillations built up, and occasionally the wings fell off. So if you're a designer of airplanes, you better know about this, right? This is an article I read in some newspaper. You notice that whenever Mexico City has earthquakes, it's a total disaster. All sorts of buildings collapse and everything. Here's why Mexico City is hit so hard by earthquakes. So blah, 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 blah. As well, many of the buildings in Mexico City have structural columns that resonate at the same frequency as the seismic waves, the earthquake waves. This matching of frequency, resonance, amplifies the shaking in vulnerable buildings, both steel and masonry ones. It's a total disaster. So if you're an engineer, you've got to know this stuff. This is from...
The library will be closing in 1 hour. The circulation desk will be closing in 15 minutes. The computer lab will close in 45 minutes. And the media services will close in 30 minutes. All reserved items and laptops are due in 30 minutes. Mahalo.
Okay, so this is actually from lab. So what we do, we have this thing, and then we have this oscillator. And we have the frequency of this exactly matching the frequency of that. And so you can see when we get the frequencies right, the amplitude increases and it just stays high because there's a little bit of damping. So this is the resonant condition. Okay, so I'd like you to watch this. This was a suspension bridge in Tacoma, Washington. It was supposed to be like the latest and the greatest, and it collapsed. It got windy, and the bridge started going like this, and woo-hoo-hoo, and it collapsed. I mean, it's not just resonance, but part of the reason it collapsed was resonance. So this is totally awesome. This was in the 40s or something like that. I mean, it's this incredible bridge. It just breaks over a river. So make sure you see that. It's really cool. Oh yeah, here's engineers designing complex systems, spend a lot of time exploring all possible oscillation modes and taking steps to avoid resonance. In an earthquake-prone area, for example, a building's natural frequencies would be designed to avoid the frequency of typical earthquake motions. So that's what they did not do in Mexico City a long time ago. A loudspeaker should be engineered so its natural frequency isn't in the range of sound it's intended to reproduce, right? Damping systems such as the shock absorbers or the mass damper help limit resonant oscillations in cases where natural frequencies aren't easily altered. Resonance is also important in microscopic systems. The resonant behavior of electrons in a special tube called a magnetron produces the microwaves that cook food in a microwave oven. The same resonant process heats ionized gases in some experiments designed to harness fusion energy. Here's one, climate change. CO2 in Earth's atmosphere absorbs infrared radiation because CO2 molecules, acting like miniature mass spring systems, resonate at some of the frequencies of the infrared radiation. The result is the greenhouse effect, which most scientists believe threatens Earth with significant climate change. At the nuclear level, the process called nuclear magnetic resonance, NMR, uses resonant behavior of protons to probe the structure of matter and to produce images used in medical diagnosis. In NMR, the resonance involves the natural precession frequency of protons due to magnetic torques. So what do you know? Resonance is all over the place. Okay, that's it. Let's just quickly let's just review. So oscillatory motion occurs in systems with a linear restoring force, F equals minus kx. We went over examples of oscillatory motion. We figured out how to figure out the frequency. We described the motion with graphs and equations, and we solved problems. With ideal systems, energy is conserved. For real systems that are damped, energy is not conserved. We talked about damping and resonance. Okay, so there's our setup. We pull the mass x equals a and we let go, and it goes back and forth, back and forth, back and forth. All right? This is simple harmonic motion. It's a special type of periodic motion. Simple harmonic motion obeys this equation, and this is the graph, the cosine. Okay, we figured if you have the x graph, you can get the v graph in the a graph, and we did that. Energy is constant. This is the potential energy. This is the kinetic energy. Potential plus kinetic equals the constant energy. And then not only that, but we actually figured out what the constant energy is. It's always 1/2 Ka squared. We figured out the formulas for the formula in the period, which only depend on basically because you know the mass. So if you know the K, you got it. K is what's important in simple harmonic motion. All right, and then not only did we do linear, we did angular. Then we talked about the damping and this crazy time constant, which makes life easy. And then we did resonance. That's it. Thank you very much.